Uh, my lecture was a little bit disjoint. I apologise for that. I didn't know that I was going to give three. It's nice to kind of start out with a quote. I start out actually every chapter in my book has a quote. It's a new quote for the second edition. But every quote is meant to be relevant to what's in the chapter. You can't always realise that when you just look at the quote. You actually read the chapter and then you say, well, you meant to say, now I understand. This isn't terribly relevant for my talk, but it does seem relevant for the entire meeting in a way. Any theory of the atmospheric circulation must be based on a theory of large-scale atmospheric turbulence. This is from an article by Eric Eadie, whom we've heard about quite a bit, of the Eadie model. He only wrote about 5 papers in his life. I guess if you write papers like him, you don't need to write more than that, perhaps. I don't recommend it as a model to follow. But I do recommend this article, which came after his famous article came after his article in 1949 on bioclinic instability. So I think there's a couple of things to note about this quote. First off, the date is 1950, so that's almost 70 years ago now. So this is one of the first articles which actually really thinks about the large-scale atmosphere as being a problem in turbulence. And same thing to note about it is that these are his words, and he puts them in brackets in this paper, large-scale atmospheric turbulence. So it's kind of the first reference that I know of to what Isaac and others call macro turbulence. So he's kind of saying, I think, that it's turbulent, but it's not just turbulence, if you will. It's not just the kind of turbulence that engineers think about as being small scale, leading to dissipation at molecular scale. So it's somehow different. So I think it was kind of a prescient comment. So I'd actually urge you to go and look at this article. Maybe you don't need to read it in detail, but it's well worth skimming just to see the insights that he has. And you can actually download it. It's hard to find, but it's actually now on my website. So if you go to my website and do a few clicks, I think there's a few. I think if you go to my website, my personal website, and there's something which says classic papers, and you click on that, you'll find this paper. So anyway, I'll talk a bit today about the structure of the atmosphere and how it responds to global warming, and work with a few others, in particular Pablo Zurita-Gotor, who was a postdoc in Princeton a number of years ago, but a continued collaborator of both me and Isaac. And I guess I'll motivate or make a statement that when you're thinking about global warming, the changes that involve thermodynamics and radiation are quote-unquote robust, and the changes that involve the fluid dynamics are less certain and less robust. By robust, I mean that if you know the parameters of what's changing and you know sort of how the forcing is changing, you can calculate the response reasonably well without defining this too exactly. So there's no exquisite dependence upon the parameters. That you change a parameter just by a little bit and you get a big response. And I kind of think there are 2 practical measures of robustness. One would be the consistency of response across a variety of models. So if you make the same change to 10 different GCMs, NCAR and GFDL and Hamburg and blah blah, and you get the same response in all of the models, then it's a pretty good indication that things are robust. So that's a kind of a practical measure. And then also, if there's some mechanism I say not structurally unstable, I don't mean that in a particularly technical sense. But if you understand what's going on with some simple mechanism, again, that's not exquisitely dependent upon parameters, and you understand it, if both of these things are true, I would kind of claim that that's this robust. And in this talk, I'll kind of illustrate it with two examples. One being the vertical structure of the atmosphere, the height of the tropopause and stratospheric cooling, which I'm going to say is actually robust. And one being the latitudinal structure of the circulation, so the expansion of the Hadley cell, the shift of the westerlies, which aren't nearly as robust. And I'll have a long diversion into the tropopause height. And one thing to note, I mean, these are interesting things to solve in their own right. If you're adding a proposal to a funding agent, they're not always saying I'd like to learn about something or understand something isn't always a good strategy. It should be a good strategy, but it's not always the best in practice. But think about the very practical thing of changes in regional circulation. And it's changes in regional circulation which will actually affect people on the, whether it rains where you are, whether it's windy where you are, whether it changes more here than in southern Europe or in Iceland. So it's these regional changes which will actually affect humankind. And those regional changes are really just manifestations of global changes in the circulation, of the westerlies shifting or the Hadley cell expanding. It's these global changes which will give rise to the regional changes. And if you don't understand the global changes, you will never get the regional changes right. So people talk about, always annoys me slightly, people say, oh, to get the regional changes right, what we need to do is downscale the results of a GCM, take the results of the GCM, feed it into some regional model with 1 kilometer resolution, and we'll translate this to a regional response. And that's all very well. You have to do that in the end. But if you don't have the global circulation correct, your regional change is going to be completely nonsense. Because it's kind of a garbage in, garbage out. You need the boundary conditions correct to begin with. So regional change is a problem in global circulation, is a little motif, perhaps. And here's a kind of robust change. This is the temperature change predicted by, this is actually the average of a whole slew of models in the CMIP5 archive, the last IPCC report. Can't exactly remember what I'm plotting here, but it's basically the temperature difference between about 2070 and the year 2000 as predicted by the average of a lot of models. And although I don't show it here, nearly every model in the archive gives a response which is similar to this. The notable things are warming here in the upper level in the tropics, bit of polar amplification here in the northern hemisphere, cooling in the upper stratosphere. The sort of lower stratosphere stays more or less the same. Upper stratosphere cools, and the tropopause, which is the black line going to the red line, actually increases in height. And it's kind of interesting. And people have noticed that. I'll talk a little bit about that. And you wonder, why should the increase in the tropopause height be associated with global warming, and we'll see in a few minutes that that's actually very natural. It's almost unavoidable that the tropopause height increases. This increase in temperature here is also fairly robust, and largely it's a manifestation of the change in the moist adiabatic lapse rate. This is actually plotting the moist adiabatic lapse rate, which is I'm sure you heard about it earlier in the summer. The temperature, the neutral lapse rate when the atmosphere is saturated, and here I'm just plotting it as a function of temperature, and it's a diminishing function of temperature going. So as the atmosphere warms, if the atmosphere warms due to global warming by a degree or so, or whatever, the moist adiabatic lapse rate will diminish. Therefore, any warming where the lapse rate is controlled by moist convection will lead to an amplification of that warming in the tropics. So that's almost unavoidable. I think we're almost certain we'll see this, and of course that will have or may well have manifestations in mid-latitudes, and it's kind of interesting to think about how this, I don't think it's really been sorted out, how this will then affect the mid-latitudes, because the temperature gradient at upper levels is actually increased between the equator and the pole, but at low levels the temperature gradient is actually decreased. So so that's going to have interesting effects on bioclinic instability. But okay, let's now think about the tropopause. Why should that go up? And just here's remind you what the tropopause is. It's the US standard atmosphere, for what it's worth. Here's the actually some observed profiles of temperature. The global average is this red dashed line. The tropics are this line here. Higher tropopause in the tropics, lower in the extratropics. But everywhere in the globe there's a tropopause. The other planets are tropopauses too. And basically, ultimately, we're saying that the troposphere, the overturning sphere, it's some region of fast dynamics where the stratification is set dynamically by whatever means that may be. Convection in low latitudes. At high latitudes it's going to be baroclinic instability, which is shifting heat upwards. So different mechanisms in mid-latitudes and high latitudes, but nonetheless in this region it's set dynamically. Up here it's in the stratosphere, it's more nearly in radiative equilibrium. You don't need ozone to have a stratosphere. You don't need any absorption of ozone. If we didn't have any ozone, we'd still have a stratosphere, we'd still have a tropopause. The structure, the temperature increase in the stratosphere is certainly partly to do with ozone, but the actual presence of a stratosphere and the tropopause are just because there's a lot of dynamics going on up here. The overturning sphere is the troposphere. The stratosphere is the layered sphere. So, okay, so...
Jeff, question?
Yeah.
Without ozone, the temperature would be constant, or
it would probably be if it is in radiative equilibrium, it would be constant, and we'll come to that. Yeah, it would be constant. So here's the sort of more or less the same picture again, but here actually are some results. This is the trend in meters per decade of the tropopause height in a slew of models submitted to the CMIP5 archive. So each little grey line is an individual model. The thick black line is the average of the models of the trend in meters per decade of the increase in tropopause height as a function of latitude. So in every single model, the tropopause height has gone up. And in every single model, the tropopause height has gone up everywhere at all latitudes. And furthermore, the increase in height, well, it's larger than the variance, so it's a fairly good sign of robustness. This is actually a plot, well, it's a statistical plot of the increase in height of the models, the mean increase divided by the standard deviation. So it's larger than 1. So it's tropopause is increasing in height. Why should that be? So to understand that, you have to understand what determines the tropopause height. So let me talk a little bit about that. The atmosphere is in radiative balance. Incoming solar radiation outgoing equals outgoing infrared radiation. And that will be the case even after global warming. Incoming solar radiation won't change very much, if at all. It's also assumed that the stratosphere is optically thin and it's in radiative equilibrium.
So when you say that incoming solar radiation is equal to outgoing,
yeah.
So you neglect the fact that currently there is a heat flux toward the ocean.
Yeah, I'm neglecting that. And actually,
so is it actually negligible or not?
It doesn't affect this argument. So let me give you this argument first. It doesn't actually affect it. It does make a slight difference. Yeah, right now there's more incoming slightly than outgoing. But it's a sign of a second order correction. So let's assume also that there is a troposphere. So let's assume that the stratification has some form like this. That there's a uniform stratification. This is temperature as a function of height. The temperature goes up to some level, and then there's the stratosphere above it. Then if you make these assumptions, that it's uniform here and it's optically thin, then it turns out that the outgoing radiation can be written as a function of the tropopause temperature only. And that's a kind of a key result. That means that the tropopause, if we know what this temperature is here, it means that the tropopause height, that this blue line, for example, will give you the right amount of outgoing radiation to match the incoming solar radiation. But this red line would actually get it wrong because the tropopause temperature would be too high. And I'll develop this argument in the next couple of slides. But the upshot of that, so just believing this argument right now, is that suppose we have a temperature structure like this today, the blue line, and then it goes up uniformly, let's say, in the stratosphere, and then we have some global warming like this, and it warms the troposphere. The tropopause temperature after the warming has still got to be the same as before the warming, because the outgoing radiation, this is strictly an equilibrium argument, but it still actually applies in the transient case, even though I won't go into that. The tropopause temperature has to be the same. So the tropopause height has to increase. And that's fairly unavoidable. How can we see that? Well, to do that we have to talk a little bit about radiation. And I'll make, these are the equations of radiative transfer. U is up. This is the upward radiation. D is the downwards radiation. Let's suppose that the atmosphere is grey, which means that the absorption is the same in all infrared wavelengths. It's not an assumption that radiation people like to make. Radiation is one of those things that you can actually calculate it fairly exactly in the clear sky case. And because you can calculate it exactly, people who actually do radiation say, why bother making any approximations? We can just calculate it exactly, or with very high accuracy. So you want to make so you say you want to treat the atmosphere as grey, and they say, oh, don't do that. But for many arguments, you can actually get a solution when it's grey, and it's so it may be a quantitatively poor approximation, but the argument wouldn't change if it weren't grey. So if it's grey, these are the equations of radiative transfer, and a two-stream, just have radiation going up and down, and tau is the optical depth. And if it's grey, B equals sigma t to the fourth. So then the boundary conditions at the top are that the upward radiation has to be equal to the downward solar radiation. So at the top of the atmosphere, U is equal to the incoming solar radiation, and the downwards infrared radiation is 0, because there's no downwards infrared radiation. So then if I solve these equations, if I first solve them by saying it's in radiative equilibrium. So if it's in radiative equilibrium, there's no net flux of radiation into any particular location. dBdz of the incoming radiation, of the downwards radiation minus the upwards radiation is 0. There's no net flux of radiation. If I solve them, these are the curves that you get, depending on what the optical depth is. So this is say, just look at one of the curves, this curve, for example. Temperature is increasing as you go deeper into the atmosphere. The more optical depth you get, the warmer it is at the surface, but of course it's the same temperature at the top because those are our boundary conditions. And you can just solve these. It's not, well, in fact, here's the solution.
Jeff,
and
question.
Yeah.
In practice, what is the optical depth, the profile?
So what I'm assuming here is that it's exponential in height. So tau is something like e to the minus lambda z, something like that. So that's what I've assumed for this calculation. And then you get, so tau has an exponential profile. And you get these solutions. And then if you say, okay, well, if tau is small, which is what it is up here, tau is 0 at the top of the atmosphere, these are the actual solutions. So the outgoing radiation turns out is 2b, where b is sigma t to the fourth. So sigma t to the fourth is OLR, outgoing long wave radiation, over 2. Well, the outgoing long wave radiation from the calculation is 2 times sigma t to the fourth, where t is the temperature here. And it's not just sigma t to the fourth, because radiation is coming from all depths here. So when you do the calculation, you end up with an extra factor of 2 there. But nonetheless, the outgoing radiation is just a function of the stratospheric temperature up here. no matter what the optical depth is. So, of course, the atmosphere is not in radiative equilibrium. The atmosphere has a, well, it might start out like this. The blue line is radiative equilibrium, but then convection kicks in, and it kicks in, and it produces this red line here. Let's say it's convection is giving you this red line here, which is going up to some height here, and then it's in radiative equilibrium up here. So the outgoing radiation is still 2 times sigma T to the 4th of the stratospheric temperature. And that stratospheric temperature is actually just the temperature of the tropopause, because the entire stratosphere is in radiative equilibrium. So the temperature of the tropopause here is, well, let's say the emitting temperature. The emitting temperature is just defined to be such that sigma T to the 4th is the outgoing long-wave radiation. But the temperature of the tropopause is this emitting temperature divided by this numerical factor of T to the 1/4. But it's exactly really the same as this argument, that the outgoing radiation is 2 times sigma T to the 4th of the stratosphere temperature, and this stratosphere temperature is the tropopause temperature if the profile goes like this. So it's not an exact argument, because you can say, well, the atmosphere isn't grey. You can say this temperature profile really isn't just like this. The stratosphere isn't perfectly thin, and so on. But those, I would argue, will be relatively small effects. By and large, if you are just assuming a radiative profile which is fairly uniform to some height, and then the temperature is actually in radiative equilibrium up there, the outgoing radiation is just a function of the tropospheric temperature. And it's very hard to avoid. So as I say here, the tropospheric temperature is fixed by the outgoing long-wave radiation. And the long-wave radiation doesn't change with global warming unless there are some wholesale changes in the cloud structure. It's a little bit similar, although I haven't really explored its connection to something called the Phat hypothesis. There's a hypothesis that Phat stands for fixed anvil temperature. That the temperature of anvil clouds, high cumulonimbus in the tropics, will be fixed. There's no clouds in this argument, really. Not explicitly. So, yes.
So, the effective radiating height is determined by the optical depth of the atmosphere. It's not really determined by the dynamics.
Yeah.
And the tropopause will be determined by the actual dynamics.
Well, we'll see. Let's come to that. That is be about the next few lectures. A few Freudian. Oh yeah. Next few minutes. Yeah, the emitting temperature somewhere here. The tropopause height is up here.
So the minute the radiative equilibrium temperature profile becomes adiabatic or lower, it should stop mixing. Assuming it's a dry atmosphere.
Yeah, well, this doesn't actually make any assumption about being dry or moist. We're just assuming some profile here.
Right.
It could be a moist profile here. Yes, and so this is this has no radiative flux. This certainly has a convergence of radiative flux. Balanced by
what
convection.
I mean to say is, if you take the pure radiative equilibrium temperature profile, which the minute the lapse rate due to the pure radiative equilibrium becomes smaller than the moist or dry adiabatic lapse rate, it should stop mixing. So there can be a discrepancy between where is the effective radiating height.
Oh, well, not necessarily. You're saying that this mixing will go up to a certain height. You're saying it could maybe go like this and then follow this profile.
If it's stable, gravitationally stable.
I don't think it will necessarily do that. No, I don't think it can do that. It wouldn't necessarily stop convecting as soon as it reaches. The convection can continue past this point. There's nothing to stop it convecting. So I'm going to. Yeah. So let me go on, and I'll give you an energetic argument as to what determines this height here.
I was talking about the slope, not where they meet. The slope of the.
Yes. So this will. The height to which this occurs is determined by the fact that the outgoing radiation needs to equal the incoming solar radiation. So let me go on and see if you, after a few more slides, see if you still have the same question. So what determines this height? You see, you can imagine another profile where it starts up here and goes down to here. Well, let me just, before I get into that argument, let me just say how, therefore, if we accept this argument about the fixed tropopause temperature, here's the profile before. If the lapse rate stays the same, you'll get this dashed red line here with the same lapse rate, and then you'll get an increase in the tropopause height. Now, in fact, there'll be an additional effect, or there could be an additional effect, because the lapse rate itself will change in the tropics. The lapse rate itself will become less because the moist adiabatic lapse rate is changing. And that's this dashed blue line here, which has a lower lapse rate. So the lapse rate itself could change, and if it becomes lower, the tropopause height will actually increase further. So you actually have two effects which are happening in the same way. One is just that the overall temperature is increasing, but the tropopause temperature has to stay the same. A second one is that the lapse rate may fall. So the change in height of the tropopause, putting those together, there'll be two effects. Just a little simple calculation says that it'll be a change in temperature divided by the lapse rate, which is just the temperature effect, and then an effect proportional to the change in the lapse rate divided by the lapse rate itself will be the lapse rate effect. You can work out what these are, because without having a theory for the actual height of the lapse of the tropopause, if we know what the lapse rate is now, we know what the height of the tropopause is now, we can just put numbers in. Turns out that, in fact, a little bit to my surprise, both of these effects in the tropics are about the same. And they combine to tell you that the change in height of the tropopause in meters is about 300 times the change in temperature per degree Celsius. So for every change, every degree Celsius change, so delta T is the overall level of global warming, the tropopause height goes up by 300 meters. That's quite a lot, actually, if you think about it, and it's certainly measurable. Because if we're imagining global warming to be about 3 degrees, a reasonable amount, it means the tropopause height on average increases by about a kilometre, which is significant. And it certainly would have implications, for example, for commercial air travel, and of which there is a lot of interest these days. So let's look at what happens. Yeah, I can repeat if
when you make this change in temperature, do you also assume that the optical depth stays the same?
I'm not no, but this is a linear argument. So it's the optical depth, it's the increase in optical depth which is causing this delta T. So I'm actually at the moment short-circuiting that calculation. I'm saying the optical depth increases by some amount. That causes a change in an overall change in temperature of delta T, and it causes a change in the lapse rate of delta lambda. I'm not specifying what that is. I'm saying I don't care what it is for the purposes of this argument. That's what's causing this delta T argument. So it is, in fact, it is. I mean, the reason we have an increase in temperature is because the optical depth increases. We have more carbon dioxide in the atmosphere, more water vapor in the atmosphere. That's causing this delta T.
Can I also ask a question here?
Yes.
You mentioned in the tropics the two terms are about the same size.
Yeah.
What about at the poles?
At the poles, I would expect this term to be larger than this term because, well, at the poles, in the tropics, you can kind of have a theory for what the change in the lapse rate would be because it's a change in the moist adiabatic lapse rate. Away from the tropics, the lapse rate, and I'll get to this in a few lectures, the lapse rate is, whoops, wrong button. The change in the lapse rate is determined by other things like changes in bioclinic instability. So I might not expect, I might expect this term to be larger than this term at high latitudes. But don't know. So that's.
I have a question too. So when one looks at the radiance curve as a function of the wavelength,
Yeah.
so we can see the trace of the curves of blackbody radiation at different temperature depending on the whether we are looking at the effect of water vapor. And so then.
You're one of these radiation people, obviously.
Sorry?
Go on, carry on.
So then. Here you are talking about this like if there is only one type of radiation and everything is emitted from the top of the troposphere.
No. First part of your sentence was correct.
Yes.
I am talking about that there is only one form of radiation, which is grey. But it doesn't necessarily, well, it comes from all levels. I mean, the fact that it's grey doesn't mean that it just comes from the top of the tropopause. I agree. What I haven't done, in a sense, a better approximation, and somebody should do this calculation, I haven't done this, is to quite a lot of the radiation escaping to space, well, a significant minority comes almost from the surface through the so-called window, and it just escapes through the surface. So that would be the next approximation. Yeah, so I haven't taken that into account, and it would quantitatively affect this argument, but I don't believe it would qualitatively affect this argument. But it would be interesting to do that calculation. Does that answer your question?
Yes, yes.
Okay.
So maybe another part of the question is if the level of low clouds would change.
This would also affect. Change. If clouds change to some degree, all bets are off. You have to think again about that too. But all other things, remaining the same, I think this is quite a robust argument. Yeah, of course, all of these effects may change things. But I think this is a fairly robust argument, and one, as it were, part of the proof of the pudding, as an English saying, the proof of the pudding is in the eating. This is the increase in the tropopause height, the change in meters. Each dot is a model submitted to the IPCC archive, and so there's a large spread in the tropopause height. What I've plotted it against here is the actual increase in temperature of those individual models over this period. TCR here stands for transient climate response. But here is just the increase in the temperature of these individual models. And you see what's happening is that the models, some models have a much higher sensitivity, and those models have a much higher increase in the tropopause height. And the actual slope, amazingly enough, turns out to be about 300 meters increase in height per degree Kelvin. So it's about, in a sense, what the very simple theory predicted. Yeah, just shout and I'll repeat it. There are some observations, but not of this extent. In fact, there have been some observations, I think they're almost a decade old now, by a man called Ben Santa, who noted the tropopause height had increased. So yeah, there should be more observations now. Yeah, that's right. There should be more. Well, the last decade haven't seen much global warming, but yes, there should be more observations. So yeah, so every model change has an increase in height of about 300 meters per degree, and as I say, implications for commercial air flights. So okay, so now let's just actually have a little sojourn into the theory for the tropopause height itself, because we can actually predict that it will increase, as I have done, without having a theory for the height itself. That's the sort of the nice thing about linear theory. Linear theory is always a good theory, provided you linearize about the right thing. And that's often the tricky part. So let's look at a theory for this, and some of this stems from a paper that Isaac did a good decade ago. So let's assume that 30 years ago, okay, time flies. Time flies. A venerable paper. So let's make some assumptions that dynamics operates to a finite height and with a specified lapse rate, like this. Just assume that. So now I'll just talk about the radiative part of what's going on. What I'm going to do is actually solve the radiative transfer equations analytically with a few approximations. And I'm going to demand that there's an overall radiative balance. And the only way you can actually achieve a radiative balance, if you assume this kind of a profile, that it goes up to a certain height and then temperature becomes in radiative equilibrium, is that you have to allow the tropospheric temperature to adjust. So if you don't, if you just specify the tropospheric height, you'll get the wrong answer, that the incoming radiation won't equal the outgoing radiation, or if you enforce that by saying, okay, the tropopause height is always at a certain temperature, you'll get the wrong balance at the ground. So the only way you can actually solve that is to allow the tropospheric height to adjust. So assuming the incoming radiation, incoming IR The outgoing IR is the incoming solar. And the upward infrared radiation at the surface is sigma Tg to the fourth, which is the temperature at the surface here. That seems like an odd kind of thing to make explicit, but actually in the radiative equilibrium result, if you look at what the upward radiation here is at the surface, it's not actually equal to sigma times the temperature to the fourth. It's equal to something else, and so you'd actually get what actually happens in radiative equilibrium is that there's a slight discontinuity between what you might call the surface temperature, which is the temperature of the air just above the surface, millimeter above the surface, and the temperature of the ground itself. But as soon as you invoke convection, that discontinuity is going to go away. So that's you're going to impose that as a constraint, and then we can obtain. We can actually solve this, it turns out, and this was actually something that I went back and forth with Pablo about over about 20 emails before we finally wrapped our head around it. But here again are the equations of radiative transfer in this grey approximation. Say that the lapse rate is given up to some height ht, above which the atmosphere is in radiative equilibrium. Now you can actually solve these equations formally. And these are the solutions. It's just basically you integrate, and it's just a formal integral solution up to some between where the optical depth is 0 and tau primed. And you can get the solution if you know what the temperature structure is. But as I say, these won't give the right answer for the outgoing radiation. So you can actually, if you want them to give the right outgoing radiation, you have to have a specific height of the tropopause. And that turns out to be given by, after quite a bit of algebra, which really would take a lecture, is given by this slightly complicated expression. And you can, if you want to find the algebra, originally it's in this paper of a couple of years ago in the Quarterly Journal of the Royal Met Soc. It's also in an appendix to the book right there. Where it's explained perhaps a little bit more pedagogically. But this is actually now, if you will, I don't know whether you call it a theory or calculation, for the height of the tropopause. And it tells you what the height of the tropopause is if you're given the lapse rate here. Tt is the temperature of the tropopause, which you are given, because that's just determined by basically how far you are from the sun. Gamma is the lapse rate. Tau sub s is the surface optical depth, which we're assuming falls off exponentially. H sub a is the goes back to Antoine's connection. H sub a is the scale height of the absorber, and T sub d is the tropospheric temperature again. So this, in a sense, is a theory for the height of the tropopause, and I've actually plotted it here. This is this analytic expression. Then this is actually a numerical solution of the radiative transfer equations, which I obtained by solving the radiative transfer equations and iterating to a solution by allowing the height of the tropopause to change. And so here's these are contours of the height of the tropopause for a range of lapse rates and a range of optical depths. And so you see what happens as the lapse rate falls. Lapse rate falls going from right to left. The tropopause height increases, as it had to earlier. As the optical depth also increases, the tropopause height increases. And as you would expect. So in the tropics, gamma is about 6 degrees or something like that. So you're getting predictions of about 11 or 12 kilometers for the height of the tropopause. So it's I actually quite like to try this out on other planets. If anybody is interested in looking at those, I'd be interested to collaborate on that. It'd be nice because Venus, for example, Venus is enormously optically thick, and its optical depth is way off this scale, and its tropopause height is many kilometers larger than this. So it would be kind of nice to know whether this formula actually worked for other planets too. There are some other theories I should mention of the tropopause heights. A pair of astrophysicists called Robinson and Catling a few years ago, and I haven't compared this to their work. I need to do that, but they had a kind of a top-down approach. They said, looking at the properties of gases, the tropopause will always be at 0.1 bar. So didn't say how high it would be. That depends on the thickness of the atmosphere, but they said no matter what, it will always be at a pressure of 0.1 bar. So that's something I kind of like to look at. There's a little, I think there's a little Python code to do this on my website if anybody wants to play with it. Yeah.
So when you say that the surface optical depth is increasing, it's like increasing the concentration of greenhouse gas?
Yes, that's right. Yes, that's exactly what greenhouse gases do.
Could you repeat again, like intuitively, how one would understand that, say, I have very high optical depth, lots of greenhouse gas, so the lapse rate decreases?
No,
like
so when I have, I'm regarding, in this plot, I'm saying the optical depth and the lapse rate are independent parameters. So when I increase, we can just vary them independently as far as this plot is concerned. If I add a greenhouse gas, I increase the optical depth. That's exactly what a greenhouse gas does, sort of by definition. And so when I increase the optical depth, the tropopause, I'm going up along this axis, and the tropopause height is increasing. And that's because, if you will, when you increase, when you increase the optical depth, more of the photons are actually coming from higher up in the atmosphere because they still have to escape to space. So the emitting temperature stays the same, but they're coming from higher up in the atmosphere. So the increasing optical depth is causing the overall temperature to increase. It's just the greenhouse effect. But the tropopause temperature has to stay the same. The emitting temperature has to stay the same. So the tropopause height increases. And that's what we're seeing in this plot. The tropopause height increases with the optical depth. And it also increases, and then there's a second effect that it changes with the lapse rate. because just forgetting about changing in the optical depth, if the lapse rate changes, and for the sake of argument start at the same surface temperature, if the lapse rate diminishes, you still have to end up at the same tropopause temperature, so the tropopause height has to increase again.
I'm slightly confused how lapse rate would be independent of the global temperature. Like if you
well, I'm not saying it is. I'm just for this plot. I'm not at all saying that it is independent. I'm saying for this plot, I have a formula here for the height of the tropopause, which is a function of the lapse rate, and it's a function of the optical depth. So let's just do a contour plot of the two. But yes, indeed, I would expect the lapse rate to change. So with global warming, both the optical depth increase and the lapse rate diminishes, so you're kind of going along this path here, from here up to here. So both effects give rise to a change in the tropopause height. So now we haven't. There's a lapse rate here which I haven't specified. In the tropics, you can imagine that it's the moist adiabatic lapse rate. Do you want to?
Yeah, I was just. Yeah, I'm worried about. But maybe you're going to explain that right now. But I'm worried about the assumption of constant lapse rate because that breaks down as the tropopause, right? That's exactly when the lapse rate is not
That's
constant
right.
anymore.
So that's right. We're only assuming the lapse rate is constant up to the tropopause.
No, but it breaks down before that, right?
Well, yes. Sure, it does.
And it also
no,
cares
well,
about
let's go back to
convection cares about radiative cooling
let's
too,
go
right?
back to the observations. Look at this observation, this black line here. This is an observation. This is actually taking the tropopause as your the origin of your coordinate system. So there's the tropopause. And look at the lapse rate. It's not terribly lacking in constancy until it gets to the tropopause. And here's actually the lapse rate in the tropics. Now, okay, sure, it's not constant from here to here.
Yeah.
But it's not that far from being constant. So if you want to do a numerical calculation and say, okay, I'm going to take into account this lack of constancy, by all means. But here I'm kind of trying to, in a sense, make a simple model, I suppose, of the tropopause height.
I might be confused, but earlier there was the optical depth was a variable, and then it becomes a single number.
No. I'm tau. That's right. Good. Thanks for clarifying. I didn't write it down here. Yes, tau s here is a single number, but there's another number here, HA. So what I'm assuming is that tau is tau s e to the minus z over HA. Okay. So it's an exponential profile. Tau s parameterizes the overall level of it. HA parameterizes how fast it falls off with height. So in the Earth's atmosphere, you have a condensate, which is water vapor, which has a very different scale height than the scale height of the atmosphere itself. So HA here, I think I've taken to be 2 kilometers. If we had an atmosphere with no condensate, HA might be the scale height of the atmosphere itself. But yeah, thanks for. Okay.
Sorry, and so that clarifies things a lot. And do we assume that as we add carbon dioxide, it all goes into the troposphere? So we're all, I mean, we can basically just, I mean, is it a linear function of carbon dioxide? Or?
No. It's not a linear function. I think it's a logarithmic function of carbon dioxide levels. But that function is known fairly well. No, it's a log. So yes, it's not linear. Doubling carbon dioxide more or less increases, and it's logarithmic. Let me just leave it at that. So let's just go one step further. Now that you criticize this theory, there'll be even more scope to criticize what I do next. Let's try and talk about mid-latitudes. See, and here's a kind of a sketch of the overturning circulation in the atmosphere, and this is would be this is the so-called residual circulation, which I think Isaac mentioned. Here's the tropopause. Kind of goes through this large, slightly exaggerated here, change in the subtropics. This is the so it's much lower here than here. It's here's the overturning circulation of this residual flow, which kind of tries to account for the effects of the eddies. You've still got a fairly well-defined Hadley cell. Here's the residual of the Ferrel cell. These are the isentropes, lines of constant potential temperature. And people have noted that the lapse rate in mid-latitudes is such that isotherms pass from the surface in mid-latitudes, say here, to about the pole at the equator, to about the pole. Say that sentence again. Isentropes pass from the surface at low latitudes to the tropopause near the pole. So this isentropic slope appears to be this isentropic slope. Empirical evidence suggests that it's actually almost constant through the seasons. So even though in the seasons in the summer there's much less pole to equator temperature gradient, the isentropic slope actually is more or less constant with the seasons. And this is related to this baroclinic adjustment argument of Stone, which is widely criticized and widely followed, and it's a different. Let me just give a sort of a very rough and ready argument for this very loose argument. That in a two-layer model, the condition for marginal stability is that the PV gradient changes sign. This is the PV gradient. There's beta, is the shear, the deformation radius squared. Thermal wind tells you that the shear is related to a horizontal gradient of buoyancy. And this deformation radius is n squared nh over f, and n has got the vertical gradient of the buoyancy in it. So if this lateral potential vorticity gradient is equal to 0, you take beta to be f over L, then this kind of rather loose scaling argument I've given here tells you that the slope of the isopycnals has to be about h, which is the height of the troposphere, divided by a, or the length, the distance between the equator and the pole. So bioclinic adjustment, and there are other arguments for this. Pardon? A is the Earth's radius in this, yeah, and there's a, I've introduced that rather magically here. But nonetheless, if you take this two-level bioclinic, it's marginally stable. PV gradient just changes sign. However way you do it, you'll end up with the slope of the isotherms, perhaps with some proportionality constant, is h over the radius of the Earth. So what that gives you is it actually tells you what the stratification is as a function of the equator to pole temperature gradient. So we can use that as a estimate of the lapse rate in here. Then we actually get with a bit of algebra, a prediction for the height of the tropopause in mid-latitudes. So we're kind of combining this, the fact that the incoming solar radiation is the outgoing infrared radiation, the radiative constraint, Isaac and others have called it, which is, you can't avoid that. Now we've actually combined that with perhaps a slightly ad hoc theory for what the stratification is, that the stratification is such that the isotherms go like this, which for better or for worse seems to be how the Earth's atmosphere more or less behaves. I'm not a terribly big fan of bioclinic adjustment because it's fairly easy to do simulations which don't give you marginal supercriticality. You can certainly get highly supercritical flow, both in a quasi-geostrophic model and a primitive equation model. But nonetheless, let's just take that as an ansatz. And that actually then gives you a prediction for both the height and the stratification. So it's actually a theory, if you will, for the height of the tropopause in mid-latitudes, and I've plotted this against the meridional temperature difference and the surface optical depth in these plots. So I am plotting the tropopause height. It also predicts what the lapse rate will be. It's kind of predicts that as the meridional temperature difference between the equator and the pole gets larger, the tropopause height gets larger. Also you have the same prediction as we had before, that as the surface optical depth increases, the tropopause height increases. And it gives reasonable sort of ballpark predictions for what the lapse rate should be. In mid-latitudes, it's hovering around these numbers, about 5 degrees Kelvin per kilometers. It's untested as yet. It's another thing one would like to do. I don't think you can expect sort of quantitative agreement, because there's all sorts of simplifying assumptions gone into this kind of a theory. But I think what you might hope is that you would see the same sense of variation if you took an idealized pyramid equation model and you change some of the parameters, I think you might hope that it would go the same way. You could also change the dry adiabatic lapse rate in a model. Dry adiabatic lapse rate appears in this formula. It's just G over CP. You could change CP in a model and see what you get. So this is kind of a long diversion, but it's kind of towards a theory of the tropopause height and the lapse rate. And back to the topic. Reverting back to temperature changes, here's stratospheric cooling. It's another very robust response. The nearly all models see it, and this was seen I think it was seen in the early simulations of Suki Minabe back in the 60s, sort of stratospheric cooling. I think the reason for it is relatively simple, in a sense that it seems a little bit counterintuitive, the fact that you have stratospheric cooling. But ultimately, without going into the radiative arguments, it's a balance between solar heating and long wave cooling. Is the radiative balance up in the stratosphere. You have solar heating because you do have ozone up here. If you increase the optical depth, so some of that carbon dioxide goes into the stratosphere, you can actually, a lower temperature suffices to provide the needed cooling. So you still have that balance, but a lower temperature will give you the needed cooling. So the stratosphere actually cools here. And there's a radiative calculation to show it, but let me go on now to things which are slightly less certain, in a sense. I mean, the increase in the tropopause height is, well, as I say, I would argue that it's robust. We understand it, or with some simplifications, we understand it. All of the models produce it. Some of the dynamical arguments, I think, are a little bit less robust. Just here's a little bit of history. Here's the Hadley cell as it was envisioned in the middle of the 19th century by Farrell.
Geoff, before you go on, so can I make a comment about the sentences that were on your second slide? I mean, you had a sentence saying that all what is related to thermodynamics is rather robust, and all what is related to dynamics is not. So if I think to this sentence, I come back to your theory for the tropopause height you just described.
Yeah.
So what are we talking about? Dynamics or thermodynamics or both?
Yeah, it's all intertwined. It's all intertwined. Making a hard and fast distinction is a fool's errand. So certainly, just if I'm going to talk about the tropical increase in tropopause height, it's both. Everything is both, so perhaps I was being a little bit overly simplistic there. But you might call this a thermodynamic argument because it's directly associated with the increase in temperature. I mean, the increase in tropopause height is just a linear function. Well, it's a monotonic function of the change in the temperature. So it's a linear function of the change in temperature. The change in the lapse rate Yes, of course, it's a dynamic thing, I guess, if you think of the moist adiabatic lapse rate as being dynamic. But the moist adiabatic lapse rate itself, I don't think I've got a plot of it, is just the neutral lapse rate when the column is saturated, and its change in temperature, the change in the moist adiabatic lapse rate with temperature is almost entirely governed by the Clausius-Clapeyron relationship. So, which again is the Clausius-Clapeyron is a thermodynamic argument. So I think you can argue that the moist adiabatic lapse rate is a thermodynamic argument. I mean, you have convection and turbulence, but
you still need to know delta T.
Yeah, you still need to know delta T. That's right. You still need to know delta T. But you know, delta temperature is a thermodynamic variable. So so I think you get into trouble if you press too hard on what is thermodynamics and what is dynamics, but I would call that a thermodynamic argument. But of course, this argument here is, if you will, certainly a dynamical argument, and there's a lot more uncertainty about that. People, if I'm at a conference of experts, and I say the moist adiabatic lapse rate will change with global warming by this amount, people would nod their heads and say, yeah, fine. If I say baroclinic adjustment is going to predict these changes in the lapse rate, you know, 5 hands going up and saying, you know, we don't believe in baroclinic adjustment because of this, this, this. So that would be more controversial. And here's, I'll finish in a few minutes. But here's just the picture of the Hadley cell as it was envisioned in the middle of the last century by Farrell and J.J. Thomson. This Thomson was actually the brother. J. Thomson was a fairly famous scientist in his own right, but his brother was William Thomson, who's Lord Kelvin. So his brother was more famous, so I tend to forget that. But this is the interesting, they envisioned a Hadley cell going all the way from the pole to the equator. And then, for reasons that were clear to them, they actually have a Ferrel cell which is underneath the Hadley cell here. So this little cell here, which is due to Ferrel, became the Ferrel cell, if you will. So that's sort of the picture in from a textbook from Wallace and Hobbes, I believe. It's interesting that Lorenz noted this ideal Hadley cell. In 1967, he noted it hadn't actually been obtained numerically or analytically, so he kind of doubted its existence, it seems. And he also noted it was likely to be bioclinically unstable. So, in a sense, is the conventional view of the Hadley cell. And here it is. Here's the Hadley cell again from observations, from a reanalysis. The conventional Eulerian picture, this is northern hemisphere winter, Hadley cell here. So certainly the Hadley cell has got a fairly well-defined width. What actually determines that width? And here's a theory due to Isaac and with some precursors by Ed Schneider. There's 3 Schneiders in our business, I guess. Ed. pointed out that you can actually, if the that you might have an angular momentum conserving Hadley cell. That if air rises at the equator, moves polewards, it can conserve its angular momentum. If it conserves its angular momentum, then its velocity will go like this. Its zonal velocity will go like sine squared over cosine theta. So it's generating a very large zonal flow. By thermal wind, if the zonal flow is smaller at the bottom, if it's in thermal wind balance, the temperature will fall very rapidly. Temperature that can't become lower than its radiative equilibrium value. So it will actually sink in the subtropics. And in Isaac's paper, there's a calculation of where it will sink. But essentially, if you want to anthropomorphize, the air gets so cold as it's moving polewards, it has to sink. And you get a prediction for the extent of the Hadley cell. And it's got a h here is the height of the tropopause. So you would expect the tropopause, if the tropopause increases in height, the extent of the Hadley cell will expand. So that gives you a prediction for how much it would change if all other factors stay the same. Hadley cell isn't quantitatively like that. And here's a simulation which Chris Walker did for me. And here's actually a zonally symmetric simulation. So you take a GCM, don't allow any eddies to form, and it's a perfectly axisymmetric. So this is, if you will, actually, a realization of what Lorenz called the ideal Hadley cell. And it actually does sink round about here. So it doesn't go all the way to the pole. It does sink here. When you allow it to form eddies, when you allow it to become baroclinically unstable in mid-latitudes, it actually, oops. How did I manage to do that? Then you get a ferrule cell. This is the Eulerian circulation, and the Hadley cell is much stronger, and it's a little bit narrower. So it does get changed when you add eddies, and of course that gives rise to another notion of what the extent of the Hadley cell will be, because if you imagine that it conserves its angular momentum, so this is the zonal wind if it was conserving its angular momentum, increasing rapidly away from the equator. If you calculate a baroclinic instability threshold, again using something like this criterion we had before, that the critical shear is beta times the deformation radius squared. I've got a factor of 4 here because I have a different definition of LD, but don't worry about that. So if you allow both beta and L and F to vary in this formula, this is the baroclinic instability threshold. So you need a very high shear at low latitudes to become baroclinically unstable, because as you approach the equator, beta is getting large. Beta is large at the equator. F is getting smaller. So the deformation radius is getting bigger. So you get a baroclinic instability threshold. And you might imagine where they overlap would be the edge of the Hadley cell. And this gives you another critical latitude Again, there's actually dependence on the tropopause height and the stratification. Although a different dependence on the tropopause height. Yeah, 2 minutes, okay. So you've got many theories. Here's another kind of a theory. That the Hadley cell actually it's not really theory, it's more of a notion. The baroclinic zone really is far distant. The main baroclinic zone is far distant from where the Hadley cell actually descends, and it's sending Rossby waves into low latitudes. Here's the zonal momentum equation. So the left-hand side, F plus the vorticity times F times V, because the eddy flux of vorticity. So if you want V to be 0, you have to have dB dy v prime v prime, so the eddy flux of momentum has to be a maximum at the edge of the Hadley cell. So so that's another argument, and I guess we don't have a sort of a single theory for the edge of the Hadley cell, and somehow all of the models, all of the GCMs know that we don't have a good theory. So they all produce their own answer because they know that they don't need to obey a particular theory. So then I'll finish on this slide, which is the same slide as I think I showed on Monday. That the scatter, this is the edge, the expansion of the Hadley cell in a bunch of models with global warming, and there's both quite a lot of scatter, and furthermore, the expansion of the Hadley cell in any particular model does not increase with the increase in sensitivity, the overall increase in sensitivity. So models which give the most global warming don't necessarily give the largest expansion of the Hadley cell. So that's what I mean by dynamics, in a sense, being. Now, I'm not saying that that we can't sort this out. I'm just saying that we, in a sense, that we haven't sorted it out yet. So these are theories, and just going back to sort of philosophical note, it's even kind of worse in mid-latitudes. So these are quite hard problems in a sense. So you have to be quite interested in them to follow them through. If we're looking, this problem has been worked over quite a little bit, and the mid-latitude problem has too. So there's less, as it were, low-hanging fruit. They're more difficult. As soon as a problem involves turbulence, it becomes hard. So let me stop on
Question?
So what do you think about the argument of the marginal criticality for the mid-latitude?
What do I think about it? Well, I don't know whether I want to possibly comment. I don't know. I mean, there's certainly something to it. I mean, if you look at, I think actually, I don't have any plots to show. Certainly there is. I think what I would say is it's a system can equilibrate by becoming arranging itself so that it's no longer unstable, and that is a way that systems equilibrate. But there are other ways for a system to equilibrate too. I mean, you can run a quasi-geostrophic system. You can impose the shear, and you can impose a supercritical shear, like in one of the systems that Isaac talked about, and it will equilibrate, and it will have some kind of fully developed turbulence, and it will equilibrate, and so it doesn't have to equilibrate. I guess sort of anthropomorphizing again, if it can equilibrate by making itself marginally unstable, that's an easy way to do it, but it doesn't have to do it that way. I don't think I can say anything more profound than that.
Why do you think that increase in tropopause height should influence the commercial airlines? Because even if you increase the height, the temperature and pressure will not change at the higher.
Yes, that's true, but commercial airlines like to travel in the lower stratosphere. So the temperature and the pressure, they like to travel above the mid-latitude turbulence. So if the mid-latitude turbulence is, if this tropopause has gone up by a kilometer, they would like to fly above that. So it's not necessarily the temperature and the pressure. I think they want to get above the turbulence. So that's why I think it might. There's so even flying a little bit higher, even if they don't fly as much higher, I think airline companies are very enormously concerned about things like clear air turbulence and so on, and they're putting a lot of money into it. Panasonic, a little aside here, Panasonic is the company that makes in-flight entertainment systems for aircraft. They've recently hired about 90 people to do weather forecasts for aircraft. And so, it was kind of, 90 people, not very many for them. But, and IBM even more. So I think, but basically to answer your question, I think they want to they'd like to get into the lower stratosphere rather than the upper troposphere.
Can I just ask quickly, the next plot, the meridional temperature gradient, or
this one?
The next one.
This one?
Yeah, so the meridional temperature difference, is it at the surface or in the upper troposphere?
That is a good question, and I think this is at the surface.
Okay, because you mentioned that in global warming.
Yes, that's right, I did mention that.
Okay.
Yeah, I did mention that, and so that's a good question, but I think this is at the surface. Yeah. There's one here too. Okay.
I was just wondering what gamma F is in this formula.
Gamma F. Oh, gamma F. Oh, that's a good question. I think it's gamma D, and I think it's a typo. I think it's a typo, but yeah, you'd have to look. Yeah, sorry.
Okay, we can continue during the discussion this afternoon if you have questions.